So now let's talk about set operators. First of all, we need to talk about the universal set, and that's really a different idea from union down here, so let's go ahead and separate that. So a universal set is a set that contains all of the elements we are interested in. Essentially, a universal set gives us a context or framework in which to work. Often the letter U is used to denote the universal set. So our first set operator is union. The union of two sets contains all the elements contained in one set, the other set, or both sets. The union of two sets is denoted A, and then we have the union B. So in our rule notation, A union B is denoted as follows. So X is the element of the universal set such that X is the element of A, or X is the element of B, or both. Okay, so we are going to associate or with union. Okay, in this case, the or is an inclusive meaning that or includes one, the other, or both. So it's not like saying you're only going to take one vacation and you've decided to either go to Colorado or New York. You know, it's going to be one or the other. In this case, you might say, what are your choices for dinner? Well, if it's a buffet, you could say you could have chicken or steak. Well, maybe there's someone out there that would have both. So that would be inclusive. All right, so we're going to do some shading of our Venn diagram. Sometimes this is more of a visual way of seeing our set operators or seeing our sets in general. Okay, so the universal set would be this entire box, right? So if I wanted to use a Venn diagram to shade set A, it would just look like this. So please note that this part of A does not include anything in set B. This part of A also has some elements in set B. All right, next let's look at set B. This is all of this entire circle. So like I just got through saying, elements in this part would be elements that were only in set B. Elements in this part right here would be in set B, but they're also in set A. Now let's talk about that operator we just mentioned, union. So remember, it's going to be in set A. That's all of this. Set B, which is all of that, or both. Okay, our next set operator is the intersection. The intersection of two sets contains only the elements that are in both sets and has this following notation. So in our rule, A union B is defined as X is an element of U such that X is an element of A and X is an element of B. So you'll notice with the intersection, we're going to see that word and. So union had or, the intersection has and. So let's shade the Venn diagram accordingly. Okay. All right, so for our next set operator, given A is a subset of U, the complement, the complement of set A is a subset of U consisting of all elements not in set A. So we have quite a few notations of the complement of A. The one that seems to be more commonly used in our notes is A and then superscript C. And then in many other contexts or books, we'll see the A prime. So formally speaking, X is an element of the complement of A if X has got to be an element of the universal set such that X is not an element of A. Okay, that's all there is to that. So what we're going to do is, to help you see this visually, I will be shading every part of this universal set that isn't a part of A. And let's do the same thing with the complement of B. That's going to be every element that wasn't in B. Okay, clearly I'm missing part of the notes here. So the last operation that we need to talk about is the difference. So given both sets A and B are subsets of the universal set U, the difference of two sets, denoted A minus B, is a set of elements in set A that remain after removing the elements it has in common with set B. So formally, if X is the element of A minus B, or X is the element of A minus B if X is the element of the universal set such that X is the element of A and X is not an element of B. Okay, so when I feel like this description is a little bit easier to figure out than this formal definition. Okay, so originally the textbook didn't even talk about the difference of sets, and they denoted the same thing as this, but I feel like the difference of sets is just an easier way of coming out with the same region. Okay? All right, so we're going to look at all of set A, but what we're going to do is remove anything that had to do with set B. So that means I'm going to get rid of that part right there. So there's the difference of A and B. So it said it's a set of elements in set A that remain after removing the elements it has in common with set B. All right, well, let's look at the difference of B and A. So B minus A. So similarly, I guess I should label, this is A and this is B. That would be helpful. So let's shade in set B here. So that's all of set B, but then I'm going to remove from it any elements that had anything in common with set A. Got a little bit overzealous there. Okay,